Good morning, everyone. First of all, I would like to thank the organizer for inviting me here. It's a great pleasure to be in Seoul again. So, today I will tell you about Lattice Enumeration, and let me explain a bit before my affiliation because it's a bit complicated. I live in Japan. I work in Japan, but I work for French institutions. So I work for INRIA and CNRS, and I'm hosted by the University of Tokyo. I often get asked a question, so this is the answer. Um, so today I'm going to talk about two works. One is ongoing with Yoshinori Aono from NICT, and the other one it was published at Eurocube 2010, so you can read the paper. And the ongoing work will be put on the ePrint very soon. So first I will give you some background, and then I will explain what is enumeration and what I'm doing here. So we need a few, you need a few background on lattices first. So in this audience, I've noticed there's a lot of mathematicians. So I think the first thing to realize when we talk about lattices is that lattices coming from very different areas of mathematics. And it's a very serious topic. So you see it in algebraic number theory, you see in sphere packing. So a couple of fields medalists have been working on lattices, and there's a lot of application in computer science and statistical physics. So there's really many different point of view you can adopt when you look at lattices. And the point of view that we're going to adopt in this talk is the cryptographic point of view. And as you know, lattices have become a very hot topic in cryptography. There's been talk about fully morphic encryption, obfuscation, worst case to average case reduction, and today is post-quantum cryptography. So what is a lattice? A lattice is intuitively a very simple object. It's just an infinite arrangement of points which are somehow regularly spaced. So for instance, in dimension 2, you get these balls of somehow regularly spaced, but here there's only finitely many. This is again in dimension 2, it would be again regularly spaced, and this would be in dimension 3. In dimension 3, they have a very regular pattern. Okay, so this is very simple. It looks extremely simple. If you want to be a bit more formal, this is what we would do in mathematics. We would describe a lattice as a subgroup of the real vectors in such a way that every point is isolated. So that's what is a discrete subgroup. So every point is isolated with respect to the others. Another way to define a lattice is to consider linearly independent vectors and take all the linear combination of these vectors with integer coefficients. So these two definitions are equivalent, and we call such a set of vectors a basis of the lattice. Okay, so concretely for us, for computer scientists, we view this would be a basis, and we would consider the lattice as all the linear combination of these rows with integer coefficients, right? Okay, so that's a lattice. So the only thing that we need to know today about lattices is something very useful, is what mathematicians call the co-volume of the lattice, or computer scientists call it the volume. So what is it? You consider any basis of the lattice. So basis would be these green vectors, or these red vectors, or these blue vectors. And as you can see, the lattice again is the set of all the integer linear combination of these vectors. Well, if you take such a basis, any basis, then you realize that if you take the determinant of the inner product, then this does not depend on the lattice, on the basis. It only depends on the lattice. So for every basis that I take, this stays the same. So that's the Gram determinant. So we also know that it's positive. So we take the square root of that Gram determinant, and that's by definition the volume of the lattice. So you can view it as the volume of the parallelepiped spanned by any basis. So for instance, if you take the simplest lattice has volume 1. Okay. So why are we interested in this volume? Well, there's a very important heuristic used in lattices. It's due to Gauss. This volume somehow measures the density of a lattice point. So what does it mean? It means that if you take a nice set of the space, then you can approximately count the number of lattice points. So you would say the number of lattice points inside this set is going to be roughly the volume of the set divided by the covolume of the lattice. Okay, so that is a very useful way to count lattice points, and that's really the central problem in geometry of numbers. So for instance, based on this, you can make a lot of guess. For instance, you could guess that if I take knowing the volume of a ball, which is a very nice exercise in undergrad math, if you take a ball of radius like this with a big enough constant, you realize that the previous ratio is going to be exponential. So you would expect that there are tons of vectors, tons of lattice points of norm less than this, and this is actually a theorem. You can prove that any d-dimensional lattice contains exponentially many vectors, provided that this constant is sufficiently large. Okay. And similarly, if you take a small enough constant, you would expect that this ratio gets very, very small. So you would expect there is no lattice point. But it's easy to build a lattice for which there is a very, very small lattice point. So these only hold for random lattices. So there's a theorem that says for random lattices, there is no point below this radius. Okay, it must be 0. Okay, so this is very useful. So these are theorems. These are two theorems. This was a heuristic, but this is a theorem. So the heuristic, we just use a heuristic to get some intuition, but this is actually two theorems. Okay. So that's it for lattice. That's all we need to know for lattices today. And now let me give you some motivation to why am I interested in lattice enumeration. Okay. So in this workshop and since the NIST competition, everybody wants convincing security estimates. I mean, especially, we'd like to do it for every post-quantum crypto system, but today we're just going to try to do it for lattice-based crypto system. And this is very difficult. Even for well-known systems like RSA, I mean, it's not so easy to do convincing security estimates. Even yesterday, some people mentioned the key size. Actually, if you look at the various estimation, it differs from one organization to another. I mean, how do you really predict the running time with the number field sieve? There's so many parameters. So that's a difficulty in any security estimate. First of all, we need to really understand the algorithm. We're not satisfied with a worst case bound. We really want to know the actual number of operations. That is very difficult, and there's a lot of parameters typically in an algorithm. So that's hold for the number field sieve. That's hold for many of these lattice algorithms. We have to tune many parameters, and it's really not an easy task. So one way to make sure that we are not too far off the target is to use numerical challenges like yesterday as a sanity check. I think that is very important. In cryptography, we already had the intersection of many fields, and sometimes there's a tendency to really focus on proof, and this is very useful. It's really good to have a nice analysis of an algorithm, but sometimes this only tells you part of the truth. What happens in practice is really sometimes very different. So, for instance, the next talk we'll talk about a very nice algorithm for lattice algorithm, which is the best algorithm in theory so far. But this is very far from the best algorithm in practice for various reasons. So this is it's very complicated. So that's why using charges is a way for us to check that what we know is not too far from the truth. Okay. So when you look at challenges, what are the most significant challenges for lattices? So the good thing is, so if you want to make money, this is the most important challenges. These are the entry challenges. This is the only lattice challenge that give you money. So my friend Nick, he solved the first one, and then he told me about the chance. So I was very excited. So with my former student, we tried to solve a few ones. So we got a few bucks, but not much. We didn't get rich. But what is nice though is that everything behaved as expected. We thought that looking at the challenges, we thought that the best method to solve these challenges should be enumeration with PQC, and we estimated the running time, and everything turned out like the prediction. So nothing surprising happened. So that's the good thing. It's really a sanity check. Okay, we understand what is going on for these type of sizes. we know roughly how much it's going to take, and it does work, okay? Another set of challenges, but this time you won't make any money with it. So it was already mentioned yesterday. This was created in 2008. So the lattices there are similar to iTie's worst case lattices. The largest dimension is a bit misleading. So with my former student, we got up to 825. Again, everything behaved roughly like we expected. So we get an estimate of the running time. We know that the next one is going to be much more expensive. And again, it's with the same method, enumeration with PQC with slight differences. Again, no surprises. Okay. But then there's another challenge where, so this one you have to find a moderately short lattice vectors. This one you have to find a really short vectors. So these are the so-called SVP challenge. Not necessarily the shortest one, but you have to find a very short vectors. And this time so I don't hold a record. That's very sad. But the really interesting thing is, what is the method used? So the method used is a bit secret. We don't really know what they use exactly. We know roughly how much time it took. And let me say a few things about this. So this was done by Japanese researchers. This is the running time given by people who solved the challenge here. So this is the curve, this is the number of coordinates, and this is the dimension of the challenge. So you have to find a very short vector in dimension 148, okay? So there's very interesting thing to say about this time. The first thing to notice is it's a very significant running time. So if you look at the largest computation, they use 200,000 core days. This is almost the same as RSA 768. So the computational power they use is really significant. I don't have access to this computational power, but still, it's very good that people devote this time to see how far we can go. So that was done in May of this year. So the amount of time spent on this lattice challenge is comparable now to RSA. I think this is unlike other post-quantum candidates, coding or multivariate. Now, the other thing which is interesting is if you look at the running time, it's not clear what is the best method. I mean, if we don't know what is being done. So in this here I know very well. This is, again, enumeration with PQC. This we did. But here, I mean, you can see it doesn't seem so different. And the other thing which is interesting is that the running time look a bit irregular. So if I come back here, you see it's not a smooth curve. Suddenly there's a huge peak. And it goes on, and then again, I mean, so it begs the question, do they know how to select the parameters optimally? Can they really analyze their method well? And maybe their actual running time should be lower than this. Okay, so we don't really know. It's very fascinating. Okay, so this is what I was interested in, is trying to understand what they're doing, and I want, again, to make a sanity check. Is everything behaving like we expect from the state of the art? Okay. So from what we know that what they use is somehow a secret variant of an algorithm called RSR, which is due to Schnorr. Okay. And RSR is kind of similar to PQC, but it's a bit different. It used at its core a routine called random sampling. So this dates back to 2003. But this random sampling is not well understood for reasons that I will explain. So this is the goal of this talk, is really to revisit it, to make it look like something we understand, okay? Oops. So this is actually the real goal of this talk, is to revisit and unify two algorithms due to Schnorr. So the first one we understand pretty well. It's called continuous pruning. So it's usually called pruning. And this was invented in the early 90s by Schnorr and his students. But at that time, so it was implemented, the analysis was not satisfactory. So in 2010, we completely revisited the algorithm, and we changed the description. And by changing the description, it led us to a better analysis, and the better analysis led us to better performances. We were able to choose different parameters so we could understand what was going on. So it was really important to analyze well the algorithm. The algorithm hasn't changed, but we really understand it better. And then there is, 10 years later, Schnorr introduced a different type of algorithm, which he called random sampling, which was not viewed as enumeration. This was viewed as enumeration, okay? And there's a lot of papers who try to analyze it, but you could argue that the analysis were not satisfactory. Actually, one of the papers actually showed that the analysis was incorrect. The assumptions could not work in practice. So this is our hope. Our hope was by describing this algorithm differently, we could obtain a better analysis and maybe get the same improvement than here, okay? So we want to understand this as well as this, okay? That's our goal, and that's what we call discrete pruning, okay? So again, I want to say that these two algorithms looked very different when they're described. They're not the same thing. So what I'm going to see today is that these are actually the two facets of almost the same algorithm. So we can analyze them in the same way. Okay, so for this I need to recall what is enumeration. So enumeration is by far the simplest method to solve hard lattice problems. So what is the goal? You're given a lattice, and you're given somehow a small ball in the space, and you want to find, so this ball is chosen in such a way the number of points inside the ball is somehow small, and what you want is you want to output all the points inside the intersection. So you want to find all the lattice point inside the ball, okay. So the good thing is it's very simple. The bad thing is that it can be very slow, so we know that in theory it's pretty bad. The running time is super exponential, okay? And typically it's going to be much larger than the number of points inside the ball. But remember, this is really the method used in records. Even though this running time looks very bad, it's very good in practice. In practice, it beats up all the other methods. So how does it work? Well, if you didn't know anything about lattice algorithm, this would probably be the method you would discover by yourself. So this is how you do it. So the trick is to use projections. So another way to say we use projection is to consider lower triangular matrix, lower triangular representation. So this is my basis. So I assume that my lattice is the set of all the integer linear combination of this row. So I take x1 times this vector plus x2 times this vector, and so on, okay? And I want to find all the lattice points of norm less than r, say. So I want to find all the integers x1, x2, x3, x4, x5, such that linear combination has norm less than r. So the first thing to do is, because I put it in lower triangular form, I'm going to look at this coordinate, right? So of course I know that x5, b5 square is going to be less than r square, right? Similarly, I could look at I can look at this square. So I know that this guy plus this guy is going to be less than r square, and so on. So I can write 5 equations, okay, 5 equations. So this leads me to a very basic exhaustive search. From the first equation, I know that x5 is limited to a few values. So I can enumerate the value of the integer x5. Now I re-inject x5 into this equation. I get an equation of a similar form. So again, I can enumerate x4. So that's how you do. You first enumerate x5, and for each value of x5, you enumerate each value of x4, and so on, and so on, and so on. It looks awful, but it works very well in practice, okay? So it's a very simple method, and just a big enumeration tree to go through. So of course, because it's not so good in theory for high dimension, people have been interested in speeding up enumeration. So assume that we don't need all the lattice points. Assume that we're happy to just find one. And now the question is, can we make enumeration faster? So for instance, if you take the Darmstadt SVP challenge, this is exactly this. They select a small ball, and they don't ask you to find all the points. It's just the challenge is to find one non-zero lattice point here inside this ball. So this is how enumeration with pruning works. Again, you have a lattice. Again, you have a ball. But this time, you're going to add another set, which I'm going to call the pruning set. So P is going to be a subset of R to the n. And this time, I'm going to output all the points in this smaller intersection. Okay? So this idea, it was not phrased this way, but it really started in the 90s with Schnorr and his students. Okay? So why do we do this? So we do it because we're going to select nice sets P so that enumeration in this smaller intersection is going to be much faster than in the bigger intersection. Okay. Of course, the bad thing is that maybe if we're unlucky, maybe this new intersection is 0 or empty, and then we get nothing. We learn absolutely nothing. Okay. So the first thing to do is to analyze when the algorithm is going to succeed. So the tricky thing is that the enumeration part is actually deterministic. So what does it mean to talk about success probability? So here I'm going to adopt the GNR framework from 2010. And the important remark is that to say that the set P is going to actually be randomized, it's going to depend on the random reduced basis of the lattice. So we can talk about success probability now. Even though this is deterministic, we can consider the probability that this small intersection is non-trivial. Okay. If it's non-trivial, we have found a non-trivial lattice point inside L inter S. Okay. So how do we estimate this success probability? So by the Gaussian heuristic, we could expect that the number of lattice points in this smaller intersection should be close to the volume of this set divided by the co-volume of the lattice. So of course, if this is big, we could expect there's a good success probability. And maybe actually, if you use random lattice theory, you realize that maybe this would be a good heuristic estimate of the success probability. Okay? So if it's very small, we get an estimate of the success probability. So we know remember the Gaussian heuristic, just count the number of lattice points inside set. Okay? So that's how extreme pruning works. It says that even though the success probability might be small, we could repeat the experiment. So what we could do is generate a new pruning set, enumerate this tiny intersection until we get something. So even if the probability itself of one shot is tiny, what matters is the trade-off, the cost of this small enumeration divided by the probability of success. Okay. So that was in 2010. Okay. That was the idea that even though the probability could be small, it can still be used to speed up enumeration. So how do we choose this set P? So the first selection of a choice P goes back to Schnorr's, okay, in the 90s. And the main idea is the following. When you project a vector, if you consider a random projection, it's going to be shorter than the initial vector. So what does it mean? Suppose that a point is inside a ball. It means that actually, when you project, you're going to consider this type of set, this smaller set inside the ball. That would be the type of set. Okay. So formally these other sets considered by Schnorr. So the basis define n subspaces, and you consider the projection over these subspaces, and this set P is formed by all the points in the space of small projection. Okay. So here you have a parameter, you have some function, and each function defines a different set. So that was an example, this set was an example of this. So in the 2010 paper, what we show is that with this choice of sets, we can indeed approximate the volume, which allows us to compute to estimate the success probability. And we can not only compute this volume, we can also compute the cost of enumeration, heuristically, and the prediction are very close to practical experiments. Okay. So this way, we can tune our pruning. We can select the best set that give us the best trade-off between this volume and the cost. Okay. So that was the situation in 2010. We had this set, and now, of course, the natural question is, can we find different pruning set that give us better trade-off? Okay. So that's the goal of discrete pruning. So discrete pruning is much simpler to describe actually than what I said before. So to this, I only need to understand the following thing. I'm going to define one I call a lattice partition. So what is a lattice partition? Consider the space, and I'm going to consider a partition of the space, like this, into countably many cells, such that the cells are disjoint, and each cell is going to contain exactly one and only one lattice point. But I want this point to be found efficiently knowing the tag of the cell. So given T, I can find efficiently the only lattice point inside this cell. Okay. So imagine you partition the space in many cells. Each cell contains only one and only one lattice point, and I can find it efficiently. Okay. So once you have this, it's very easy to define a pruning. What do you do? Well, you have a partition, so you have infinitely many cells. So what you're going to do is you're just going to select a finite number of cells. Okay. And what you do is you enumerate this intersection by enumerating all the points inside each cell. For each cell in your finite subset, you select the points. It's very easy. So my pruning set is just a union of cells of the partitions, right? A very easy definition. So how much does it cost us? Remember that finding the lattice point inside the cell, that's polynomial time. So this is polynomial time, and you do it for as many cells as possible here. So the running time is essentially the number of cells, so it should be U here, divided by the probability of success. Okay. So that's a very simple form of lattice enumeration. Just select finitely many cells and do this. So the only problem is that, okay, this is very easy to implement. Our only question is, how do we compute this volume? So to estimate this probability of success, we need to be able to compute the volume of the intersection of a ball with a cell. So it depends, of course, on which type of partition we're going to use. Can we compute the volume of a ball intersected with a cell? So what kind of cells could I use? So the simplest example could be to take a fundamental domain. So what is it? So here you see I partition my space into cells, and you can see from this picture that every cell contains just one lattice point, right? So this could work. Or if I change the basis, you can see that the cells look different, right? So in general, if you take a fundamental domain, so a fundamental domain is just formally in mathematics, it's a measurable subset such that the space is covered by translation of the fundamental domain by lattice points. And you want the interiors of this to be disjoint. So every fundamental domain give us a lattice partition. We name the cell like this. So the cell of tag T will be T times B plus D. So that I can form all the lattice points. So V is of the form T times B, where T belongs to Zn. Okay. So this would be a way. This would be a lattice partition, but it looks pretty useless because that means that for any cell, I already know the lattice point. It's T times B. So it looks a bit artificial. It looks like we're not doing anything smart here. We already know the lattice point. So why would it be useful? So to get a non-trivial lattice partition, we have to use Gram-Schmidt. So remember, Gram-Schmidt organization is you take vectors here, And the Gram-Schmidt vector, the ith Gram-Schmidt vector is just the component of bi, which is orthogonal to the previous vectors. Okay, so in other words, you could say I project my vector over the orthogonal complement of this subspace. Okay, so this is the bi star. That's the only thing I need. So to avoid the previous problem, I can choose a set which is a fundamental domain for two lattices. So what does it mean? I take a basis of the first of my original lattice and I consider its Gram-Schmidt vectors. And it's well known that this parallelepiped, the sum of the xi bi star where xi is between -1/2, 1/2, is a fundamental domain for both the lattice and the Gram-Schmidt lattice generated by the Gram-Schmidt vectors. So this way we can select this time again Zn as the set of tags, and the cell of each integer vector is just t times b star plus this domain. So what does it mean in a picture like this? So this time my cells are like boxes. You can see each box contains only one lattice point. Right? So it looks correct. So you could say, how do we find the lattice point inside the cell if we really want to find it? So that's essentially Babai's algorithm. So Babai's algorithm, given a point, I can find the lattice point. I know that in each cell there's a lattice point. How do I find it? That's Babai's algorithm. So now here's the thing that is really interesting. So after reading this, so the people who did the records for the SVP chance, they published a paper, and by reading this paper, it turns out there's something implicit in what they're doing. They use a different partition with natural integers. So instead of having Zn, now I'm going to partition my space using the natural integers. So there's a formula for the cell, but the best is to show you the picture. What do the cell look like? Before we used to have nice boxes, right? The partition they use is different. Implicitly, the partition used non-connected cell. So it looks like this. So what is it? This is the same as before. The green one is the one that we had here. But now, the one before is split in two. So the one on top is split in two. This part and this part. This part goes with this part. So I put in the same color, the same cell. So this was the first cell. The second cell could be this one with together, this one with this one, this one with this one, this one with this one, or it could be even 4. 1, 2, 3, 4. This would be the white cell. What has changed? What has changed is you have sliced the previous boxes into exponentially many smaller boxes, and you are rearrange them into a box of cells of the same volume. So for instance, let's take the yellow cell. The yellow cell, if you put it together, the volume is the same as this one. For the green one also, it's the same. This one plus this one is the same surface as this one. It's just they are arranged geometrically differently. Okay. So remember before, we're going to select, in our pruning, we're going to select a finite number of cells, and we're going to enumerate all the lattice points inside these cells. So by doing this, you realize intuitively, this looks a bit better because you're intuitively closer to the origin. Okay, you can see if you select your cell, you're going to be closer to the origin. So this is it. This is a different partition, and now we're gonna. The key question is, how do we select which cell we're gonna take? Are we gonna take the white one? Are we gonna take the gray one? Which one should we pick? Okay. So this is the way that we now can view revisited Schnorr and the Japanese method. So Schnorr used special cells like this. And the Japanese researcher used a different cells. Okay? But the most natural cell would be the one that maximizes the volume, because you want to maximize the success probability. So to do this, if we want to maximize the volume, we need to be able to compute this volume. So here is something very interesting. We have a very easy to implement method. The problem is that if we want to estimate the success probability, we need to solve one technical problem. We need to approximate the intersection of a ball with a cell for many cells. S is a ball, and this cell is a box or a union of symmetric boxes. So you saw it here. Here, this is a box, and here is a union of symmetric boxes. So of course, if you take a ball, we don't need to compute each intersection. We just compute one small box and compute the intersection and multiply by 4, right? So here's a technical problem. How to compute the intersection of a ball with a box. So we take a ball, say the unit ball, take a box. Can we compute the intersection of a box and a ball? So the first reflex is to use the central limit theorem, because when you take a point inside a box, you can see that its norm is a sum of independent variables. So you think that maybe we can apply the central limit theorem. So it turns out we can do it if the box is balanced. If the box is balanced, the central limit theorem gives us an asymptotic formula for this volume. Unfortunately, our boxes are not really balanced. So why is this? They come from reduced bases, and typically the gram sheet vectors decrease geometrically. So it doesn't exactly work. But the more reduced the bases, the closer we are to the central limit theorem. So let me give you some graph. So this would be, things were nice, we would have the normal distribution. But in practice, because our box are not balanced, if I take the NL basis, it looks like this. Unlucky. So it doesn't work. What happens if I take a better reduction? So this would be LLL. This would be BKZ, so you get it's better. But it's still far away from the central limit theorem. Okay. And unfortunately, if I increase the dimension, it gets worse and worse. So I take the same quality of bases, and I increase the dimension, I get further and further away from the central limit theorem. So that's bad. We cannot have a nice formula, asymptotic formula. So instead, we want to do an exact computation. So first, we realize that it's possible to obtain exact formulas at infinite series by generalizing previous work done by mathematicians in the 90s using Fourier transform or Fourier series. Okay. So these are nice formula. Unfortunately, they don't converge quickly enough. So in practice, it's not good enough. This is too slow. So in practice, the best method we have to compute the volume of a box with a ball is to use the fast inverse Laplace transform. And by looking at literature, it turns out that this method, due to Hosono, is the best for what we need. So in dimension, say 100, it takes less than 1 second to compute one such volume. Okay. So now it's good. We can really compute the intersection of a ball with a box in practice. And this is why it's useful. So this is the prediction from the volume of the success probability, and you can see that it really matches the experiment. So now we can see that from this volume computation, we get a very good prediction of what's going to happen. Are we going to find a short vectors or not? Okay. I don't have time to explain these other points, but it shows that this volume computation is very useful. Okay. Now, he explained why the Japanese method is much better than Schnorr's. So intuitively, as I said, we want to select the cells that maximize the volume. So this is the volume of the cells selected by Schnorr. These are the volumes of the cells selected by the Japanese researchers. You can see they have much bigger volume. So they're better. And these are the distribution of these volumes. So you can see it's clear from this picture that this is going to be much faster than Schnorr's method. Okay. But now, of course, we would like to maximize, we want to find the best cells, right? So we know how to compute one volume, but still, I mean, it's fast, but it's not fast enough to do millions of them. So the good thing is that there is a good heuristic to select good cell, which is, given a cell, it's very easy to compute the expectation of a point inside the box. Okay, there's a formula. So if you want to find the cell that minimizes this expectation, it can be reduced to finding the closest lattice point in some different lattice inside a positive quadrant, because we want the TIs to be positive. The good thing is, so now it's something crazy. We're doing enumeration on a lattice using another enumeration. So it looks crazy. But the good thing is this lattice is very special. It has an orthogonal basis. So in practice, this is extremely fast. It's maybe 1 minute. Okay, so even for very high dimension, it takes 1 minute. So it's very easy to select the cell with the best expectation. Okay? Is it good enough? So this is the correlation between the expectation and the volume. So here we selected the best cell with the best volume. Okay? And here the expectation. So you can see that there's a very high correlation between the expectation and the volume. So if we are really only interested in finding the best volume cell, it's enough to consider the best cells with best expectation. Okay? So this is very fast in practice. Now there's a trick. So when I was, like many people, I was fascinated by the US election. So when I was following the election, I realized that we have a problem which is similar. So I told you we can compute one individual volume very quickly, less than 1 second. Very good, but we want to do it for millions of them because we would like to select really the best cell out of many choice. So what we want is, we want to compute this gigantic sum, okay? And we know how to compute each term well, but we have to do it so many times, it's too expensive, right? So when I was watching the election, I realized, well, we can do the same thing as election. Instead of computing exactly this sum, let's just select a few thousand cells and extrapolate the sum. And we have some additional information because we know how to order by expectation, and that improves the approximation. And it turns out it works very well. So using just a few thousand cells, we can get an error less than 1%. So that's the good thing. Our cells behave better than American voters. So in the election, as we know, the polls were very far away from the truth. But here it works very well. And of course, I mean, the impact is smaller. We only want to approximate this. We don't care who's going to be really elected, right? So now it's good. We can really approximate the success probability of discrete pruning, even for millions of cells. So that concludes my talk. So what I show you that both Schnorr's algorithm from the 90s and the 2000 can be viewed as prune enumeration. And in particular, the second one, we introduce enumeration with discrete pruning, which is really an alternative description of random sampling. So even though random sampling was not viewed as enumeration, we can view it as enumeration. And by doing so, we can finally analyze this algorithm in the same way as prune enumeration with continuous pruning. So we get better assumptions for the analysis. We get, this time, the first time, accurate predictions. Before, we never had accurate predictions. So hopefully, we're going to be able to select better parameters. So in the past few weeks, we've done quite a lot of experiments to find out if discrete pruning is better than continuous pruning. So this is what we get so far. So we did test with LLL basis and BKZ basis, and what our simulation indicates is that if you don't want to spend too much time on enumeration, discrete pruning is better, much better than continuous pruning. But if you're willing to spend a long, long time for enumeration, then continuous pruning is better. Okay, so that's what we get right now. However, there's a catch. We're using typical reduced basis. And what is apparent is once you want to maximize the intersection of a box with a ball, maybe we need a different basis reduction. maybe LLL or BKZ is not what you want. Maybe we need to invent a new reduction algorithm that targets discrete pruning. And maybe then this balance will change. So this is a work in progress, and actually, if you read the Japanese paper, it seems that they're trying to target the same thing. They're doing something different from BKZ, and maybe that's what we need now. We need to focus now on the reduction algorithm, how to take advantage of this different enumeration routine to get a better running time. And that's all I wanted to say today. Thank you for your attention.
Now we have time for questions. There are no questions in the same flow system. Is there any question or comment?
In your election tree, does the number of sampling points does it increase exponentially with the dimension?
So that's a good question. So, oops. Oops, no, it doesn't work. Well, okay, we're stuck. I didn't check if I go very far because to check the methods, we only use the maximum I think we used was maybe 1 million cell. So I don't go further from that, like say 100 millions. I don't know what happens. And I haven't looked yet at the literature because I'm sure there's some mathematical results about that. So of course we need to know something about the distribution of the volume to explain why it works so well. So I don't have any intuitive thing about what is the asymptotic numbers that is enough to guarantee, say, a 1% error. But it looks, from practical experiment, it looks like very small numbers give you already a very good estimate. Like if I restrict myself to say 10% error, it was even smaller than that. So yeah, if you know the literature about this election sampling, what are the sufficient conditions to guarantee these type of things, I would be interested.
Okay, thank you for nice talk. So that's right. You said so new type of base reduction could be better for discrete pruning.
Yeah.
So what kind of base reductions? So deep insertion of LLL or some special choice?
So this is the thing which is, I think, very interesting, which is if you look at normal enumeration, so we know already that for normal enumeration, what we do with LLL and BKZ is not optimal. What we'd like to do is we'd like to find a basis that minimizes the volume of the first, say, half vectors. But we don't know how to do it. So we do LLL, we do BKZ, but we don't really target the right problem. Here we know what is the problem again. We want to maximize the volume of a box with the ball. So that's what we want to do. So again, maybe this can be more easily done than minimizing the half volume. So this is what is interesting. Maybe the method itself is not better, but maybe the basis reduction will be easier to get than for the other method. And maybe overall we do gain something. We already know we gain something if we do a short enumeration time. That is for sure. So yeah, now you're asking what kind of method we could do to target this. I think, this is working. There's a lot of people here, so I'm expecting people here will try to solve this problem. And so I think the Japanese people have some method, but we don't really understand it because it's not really in the paper. So we have to wait for their forthcoming papers or find it ourselves. So that was just one part of the algorithm. We need to find the other part now.
We have a question from SimFlow system. The question is, what is your intuition about what a good basis for discrete pruning would be like?
So intuitive. So again, remember that this basis generates boxes, and you want the box to be So one good thing that you could do is, so that's what they try to do. Oops. So I said there's a correlation between the expectation and the volume. So if you look at this, so intuitively one way to find the best basis would be to find a basis that minimizes this expression. Okay. So one easy thing you can say is that this term includes this constant times the bi square. So one way to see this is to say, okay, if I decrease the sum of the Gram-Schmidt norms, I can decrease this value. It's not exactly the same, but at least if I can decrease the sum of square, I do decrease the expectation. So I would hope that maybe the volume is going to be better too, right? So that's actually what the Japanese people are trying to do, decreasing the sum of the Gram-Schmidt norms, okay? But you can see from this that it's not the only way to do it. It's a more general formula, and this is only the expectation. So yes, there's a correlation between the expectation and the volume, but it's not exactly the same. So, I mean, this is really interesting question. Yeah. So, minimizing the sum of square, I don't know if that satisfies the question or not. So that's one way of doing it.
Now it is time to end this session. Let's thanks to the speaker.